I don't care. You're acting like I care. All right.
Yeah, every test is either like
should go in there
17 or
Tuesday,
18
Mr.
or
Early.
20.
We're not busy.
Those are the three scores.
I noticed that, Lucas.
Everything.
This is being recorded too, Lucas.
Okay.
Okay. I just want you to know.
Okay.
Just want you to know.
Well, isn't 5 on my worst test grade? So
I think the extra
I don't
days,
know.
well, at least for me, those extra days definitely
I
help.
want like
I thought they helped us. That is not like. I just made a stupid
It was
mistake.
on the.
I think talking about it during 0 hour helped as well.
What up, Kellen?
Hey Kellen, I bombed my physics test. Good luck.
I'm sure Kellen's like happy right now. He hears this.
All right. I think the batteries in this thing are dead. Hey, look at that.
No.
Do we have 0 hour next week? Since there's no school Tuesday?
I knew someone would ask that question.
Oh, that
He
is
was
a
just-
good question.
he was
Lucas.
just
That is a
hoping.
good question.
Well, I mean, I'll
Dewey has
tell
some
one way or
0 hour
another. I
next week.
just don't know.
I mean, I don't think it'd be fair
Let's
in the
have
second
0 hour
hour
just so
we
we
were just
can get
learning so
ahead.
much more. In the first hour we were just learning so much more than then.
Yeah,
Okay.
that seems unfair.
So this unit is called electrical potential.
What unit number is this?
11.
11, thank you.
All right. So what I want to do today is give you a very, very, very short introduction and set you loose on some reading and then a couple of problems.
Problems, not questions.
Problems. Si, senor. Okay. So electrical potential is kind of weird. Okay. It's you thought Gauss's law was weird and smoky and kind of like, I can't grab hold of this. This is worse.
Should you move your license thing to
Doesn't bother you.
a little bit? It was different.
Oh.
Okay. Now, what you got to do is kind of think about electrical potential as something that is a property of the space inside of an E field. Okay? Now, we can make sense out of it if we think in terms of gravity for a second, because gravity makes more sense to us than electric fields. So, if that's the ground, and there's Josh,
Hello.
and next to Josh, on the ground, I have the physics brick, and I have the physics marble. And they're both sitting on the ground, even though the marble looks like it's floating. And we lift it up. We lift up the brick, height h. We lift up the physics marble, same height, and we say to ourselves, which one has the bigger potential energy? The physics marble or the physics brick? The physics brick. Because potential energy is mgh. Okay? If we take a second marble and a second physics brick and say put them over here, we'd say, oh, this physics brick, the higher physics brick, has more potential energy than the lower physics brick. And we'd be right. Okay. What if we imagine that the gravitational field of the Earth were like this field, like it changes space, and if we do it like we did with electric fields, we'd say put a point mass in the field instead of a point charge. Put a point mass in the field. Which way does the field apply a force? And it's always this way. So if we were to draw field lines, we'd say, ooh, that one went right through Josh. Sorry, Josh. Skewered him.
All right.
Okay. We'd say field lines straight down toward the Earth. Now, how much potential energy does this spot right there have? 0. Because there's no mass there. I didn't put a physics brick there or a physics marble. It doesn't have any. But what if we decide, okay, I'm going to find the potential of the physics brick. Not the potential energy, but the potential. And this is how it works. We're going to say the potential is the potential energy divided by the amount of mass.
Is that VG?
Yep. So I'm calling that V sub G, gravitational potential. Now, if I did that, we'd have mgh over m. We just have gh. So at this level, which would have more gravitational potential, the brick or the physics marble? They'd be the same. Okay. At this level, which one would have more gravitational potential, the brick or the physics marble? They're the same. See, now it becomes a property of the field and not a property of the object you put in the field. Any object you put at that level has that potential. How you doing, Dr. McGraw? You were looking at me, gave me that look like, this is weird. So now, even without an object there, pick a spot in the field, like right there, and say, what's its potential? Oh, it's GH. It becomes a property of the gravitational field, not a property of an object that you set in the field. Yes?
But the way you're doing this right now, it's like linear. Like the farther away you are,
Uh-huh.
it's just like...
Okay. So what we're going to be doing when we do it with charges, you're right, it's not going to be linear anymore. But we've done this before too. We've said, okay, here's the planet Earth. Okay. The gravitational field lines, if we modeled it that way, we don't, but if we modeled it that way, we'd say it's got gravitational field lines that look a lot like the electric field lines of a negative charge. Okay? All masses are attracted to it. Unfortunately, with gravity, there's only one kind of charge. M, right? All masses act like they have the same mass charge, if you think of mass as a charge, which is an interesting way of conceptualizing mass. But anyways, if I put a mass right here, it's going to have a certain amount of potential energy. So if this is the Earth, and this is Ralphie test mass, we'd say potential energy of Ralphie test mass is negative G m over r, if you recall. That was a while ago. But if I want to know the potential of this spot, I'm going to say the potential of that spot is U over M, or negative G big M over R. That's a negative sign there. So if we don't have a thing called gravitational potential, but if we were to come up with it, we'd say, oh, I don't care who's at this spot right here, whether it's Ralphie the test mass or nothing. That spot has a potential of negative G M over R. And so I could say every spot has the same potential. I put Ralphie at any of those spots, and he's going to have the same potential energy. All of these spots have the same potential. All of these spots have the same potential. So by dividing by the mass, we make it a property of the field around the Earth, the gravitational field around the Earth, rather than a property of the object you set in the field. Now, this is not new. Remember what we did with electric fields. So we said, look, I've got a charge here, Q, and it's got field lines emanating in all directions. And we defined the E field as not the force on little test charge Ralph, because it would be really cool if I could. If I could say, hey, look, the strength of the E field is the strength of the force on Ralph. But then, McGraw comes along with test charge Bob. And, test charge Bill. And Bill's got twice the charge of Ralph, so he's going to have twice the force on him. And we go, oh, crap. McGraw's getting a different answer than me. He's going to get another one wrong on the test. No, just kidding. Sorry. Too soon. All right. So, I couldn't resist.
That's okay.
All right. So what we're going to do is we're going to divide by the charge. So if I divide by Ralph, I've got a certain amount of force I'm dividing by. He's got twice the force, but also twice the charge. So, whoa, this works. Now, this is not new, right? We did this 3 chapters ago. we said, okay, this is how we're going to define E field. Well, we're going to do the same thing. We're doing the same thing with potential. We're going to say, look, this little dude has some potential energy. Okay? U. And if we put Bill in there, he's going to have twice the potential energy. So what we're going to do is we're going to take that potential energy, divide by the charge, and call it V. We're going to say the potential, not the potential energy, but the potential of the field at that point is the potential energy that a little testy charge would have if you set him there, divided by the amount of charge you set there. And now that value V is the same for anything you set there, whatever charge you've got. And by the way, if you want to know its energy, all you do is you take the potential there and multiply it by the charge, right? Just like before, if you want to find out how much force was on the charge, you just take E times Q. We're going to say, okay, if you want to find out how much energy, potential energy he's got, we're just going to take the electrical potential multiplied by Q. And bammo, you've got it. Now, that also means we can draw these equipotential lines that say, all right, anywhere on this dotted line, we've got the same potential V. Anywhere on this dotted line, we've got more potential. Anywhere on this dotted line, we have the same less potential than the other dotted lines. Okay, so these equipotential lines become something we can add on to our field lines and say, all right, anytime we put Ralphie on one of those, anywhere on that line, he's going to have the same potential energy. How you doing? I'm spending a lot of time on this because it's simple, but it's elusive. You think that that spot right there, even though there's nothing there, that spot has a number attached to it called its potential. Okay? It's a spot in space, yet it's got this vector attached to it called its potential. I beg your pardon, it's a scalar. It's a scalar attached to it called its potential. E is a vector, V is not. Now, what we'll find out later, too, is that an electric field with all these potentials everywhere actually contains energy, even if it contains no charge. If you are in an electric field, that field has intrinsic to it some energy. Now, there's electric fields everywhere in space. That means the space you live in has stored in it a little bit of energy. The vacuum. If I pump all the air out of this room, we're in a vacuum, but between you and me, there's energy. Are there electric fields in this room? I mean, there's wires carrying current to these lights and to the computer. There's the Wi-Fi system, which takes the, are you paying attention? Which is taking the ambient electric field and it's jiggling it. It's shaking the electric field and using it to send information to your Chromebooks or my laptop or whatever, or your phone. Is that a weird thought? That between my two outstretched hands, there's energy there. Sometimes it's called the vacuum energy.
You make like fireballs.
Yeah, you just like, you like harness it somehow, and you're just like.
Well, if we could harness it, that would be a source of, an infinite source of free energy, right? So in some science fiction movies, novels, they talk about the 0 point energy. We're stealing energy from the vacuum and using it to power our ship to go to Alpha Centauri. Okay? That's science fiction. Right now the theory is, no, you can't tap into the 0 point energy of the universe. But, you know, who knows? They said we couldn't fly either. Okay. Now, crazy stuff. I kind of got off my rocker here a little bit, so hang on. There we go. So what we need to do in the next couple minutes is get a little bit more formal about this, because you got the concept. Now, how do we put it to action? Oh, by the way, check this out. The units of potential energy are joules. Oh, come on, Emily. Kellen's laughing at me right now. I need a lowercase j. And this is coulombs. Okay, so that means the units of potential are joules per coulomb. Yes. His name was Alessandro Volta. So a joule per coulomb is a volt. Dun, dun, dun. You've heard of those before, huh?
Yeah.
Okay, so a volt is a joule per coulomb. Okay, so it's a little awkward. The symbol for electrical potential is a capital V. And the abbreviation of its unit is a capital V. So 1 volt, V equals 1 volt is a thing, you know. V equals 1V or 5V or whatever. So it won't be as confusing as it sounds, but it's a little awkward. All right, so let's do an example, and this is an easy example. So suppose that I've got this big long sheet of charge. Okay. Reason I use a big long sheet of charge is because that way the field lines are parallel. And it makes for a much easier problem for now. Okay, field lines going the other way. There we go. All right. Just to keep things light, let's say that the E field is 200 newtons per coulomb. And I take a charge right there, and I move it from there to there. Okay, let's say that is a charge of 50 microcoulombs. And let's say I move it 2 meters. Question. It's a complicated question. Is this charge gaining or losing potential energy? Notice I didn't say potential, I said potential energy, the old stuff that we've had in the past. It's gaining. How do you know, sir?
Because the field lines are moving in the opposite direction that you moved it. It's like
Okay.
field lines are pointing.
Okay, so he's kind of swimming upstream.
You had to do some, you had to put in energy to get it there.
Okay, I had to put in some energy. When I put in energy, I'm doing work. Am I doing positive or negative work when I move the charge from here to here? Am I doing positive or negative work? Which way is my force?
Positive.
The force I apply is toward the...
To the left.
Okay, and the distance, the displacement I apply is in the same direction, so I'm doing positive work. Okay? But you were actually thinking the right way, because the technical definition for potential energy is that work done by the field is equal to the negative of the change in the potential energy. I started with me because it's a little easier to think about, but if I move this charge from point A, I better label this because Kellen's watching. There we go. You can't see where I'm pointing. If I move this charge from point A to point B, is the field doing positive or negative work?
Negative.
Negative. Because the field is applying a force which way?
To the right.
And, thank you for saying to the right. And we are moving the charge to the left. So this work being done by the field at the moment, in this example, is negative. Therefore, it'll cause a positive change in potential energy. That's the technical way of defining change in potential energy. It's not what I do, it's what the field does. But it's kind of easier to think about what I do, because if I do positive work on something, I'm putting energy in. And if I'm doing negative work on something, I'm taking energy out. So unofficially, it works. But officially, yeah, I know the pun. Officially, we have to look at not the work done by an external agent, but the work done by the field. Okay, back to the problem. How much work is being done? Okay, because the field is uniform and the force is not changing, I can use the good old F delta x times the cosine of theta. Okay, and because the angle between the force that the field is applying and the displacement is 180 degrees, I'm going to say, look, dudes, it's going to be negative EQ times delta x. E is everywhere the same, so no integration required. So I could, by sticking the numbers in, calculate the change in potential energy of this charge. Okay. Now I could also calculate the change in potential. Right?
Divide out the charge.
Just divide by Q. Right? So I could either do that now or after I calculate delta U, but let's do it now. I could say the change in potential is equal to the change in potential energy divided by the charge. Okay, I'll drop the negative signs because there's one on either side, so even Steven will be happy. And I'll say EQ delta X over Q is just E delta X. So if I want to find the potential between those two spots, I could just say E times delta X. So just for fun, let's do it. We're going to say 200 newtons per coulomb times 2 meters. And I'm going to get 400 newton meters per coulomb. Okay, this is delta V. Okay, notice this technique only works if the field is uniform. When it's non-uniform, don't do this because the E will be different as we move the charge. If the E changes, we need some integration, and we'll take care of that on Wednesday. Now, one note here. What's a Newton meter? Joules. So I've got 400 volts. All right. You can now see that E up here is sometimes not, instead of saying these weird Newton per Coulomb units, sometimes they use volts per meter for E. The units of electric field are more commonly given as volts per meter. All right, so read chapter 24, do problems 2, 3, 5, and 6 as best you can. If you get stuck, just say, oh, Mr. Everly will help me on Wednesday because we didn't do any examples other than this one. Chapter 24, do problems 2, 3, 5, and 6. Thank you.
Do Thursday or do Wednesday?
Do Wednesday as best you can. See if you can make sense out of this. So once you read the chapter, this should be pretty clear. But if it's not, don't worry. We'll take care of it.
Okay.
Did you see they've just discovered this thing called gravitational waves?
Yeah,
Oh, yeah.
I just saw that.
Yeah.
That was
You watched that
amazing.
video?
I didn't watch it. I just read a little bit about it on Reddit.
There's one on like,
Bye, Mr. Everly.
Take care.
Have a
See ya.
nice
like New
weekend.
York Times. Did you see that?
Yep, I'll see you.